Now things will be recorded.
Okay, so welcome to the weekly colloquium of the School of Astrophysics. We are glad to have Dr. Kaustubh Chandra from Penn State University as our speaker today. So Kaustubh did his undergrad from NIT Rourkela, where he started as a civil engineering major. And after a couple of years, he realized that he likes physics more. So he changed his major to physics. And after finishing at Rourkela, he went to he got several PhD offers, and he chose to go to IIT Bombay, where he worked on his PhD thesis with Professor Archana Pai. And after his PhD, he went to Penn State University for his postdoc, which he is almost finished with, and he will join the Albert Einstein Institute in Potsdam for his second postdoc in the coming months. So, Kaustubh today will talk about a particular gravitational wave source, which has puzzled the current community of gravitational wave astronomers. So, we'll hear from Kaustubh about how they are planning to, they are trying to understand this strange phenomenon.
Yeah, this is my first time. The last time I was like 15, 16 years ago, I just helped my sister carry a bag full of books after she had completed medical science and to sell them. So it's nice to be inside. Before I begin, I just want to let you know that feel free to ask me and interrupt me during the course of the talk. As you will soon realize, I speak a way too fast for people to understand. So if you slow me down, just raise your hand and ask me questions. That's the best way to stop. Now, just to introduce you to this event, this is GW231123. In America, people read the date in this way, not this way. But anyway, no matter how you read, this event was discovered on 23rd November 2023, just a day after my birthday. So probably the god, like gods of gods. Yeah. So, huh?
The other famous one is 170870.
Yeah, that's a binary Newton star event, and that event happened on Gayatri's birthday, who was also Akshana's student. So, good things happens in good days. Anyways, so if you look at my talk title, I call it a safe shifting column, and this is simply because this event has puzzled us a lot. In fact, even though we have detected this event on like November 2023, this event actually became public last month, which means we spent quite a lot of time trying to understand this event. But unfortunately, we haven't done a really good job. And I'm saying it as part of the paper writing team. So whenever a gravitational wave event is detected by the collaboration, a few selected people have are generally allocated this event. They study this event in detail. They do all sort of science as much as possible. And then this event become public. And as part of the paper writing team member, I can tell you that we haven't done a good enough job. And I will tell you why this is such a case. But before we do so, let me start at the right of the basics. So I think you can all see the screen. Please let me know if you are not able to do that. So gravitational waves are generally introduced in general relativity as dynamically changing space-time vectors, which travels at the speed of light, and they can be produced by any sort of accelerating non-axisymmetric mass distribution. Whether they will be detectable or not is a different question. Now, current and future generation experiments such as LIGO in US or space-based experiments such as LISA, Tianqi, etc. All these are based on the principle of photon timing. If you've done a course in optics, you probably know about Michelson interferometer. These are like big Michelson interferometers with Fabry Perot cavities. And they are all based on this principle of photon timing. They just try to measure the distance between 2 points using laser waves. And using these type of detectors, you will be able to detect different kinds of sources. They should be able to detect it, but currently we are just detected sources which consist of merging black holes, merging neutron stars, or a black hole neutron star. But putatively, they can also detect supernova explosion. They can also detect rotating pulsars. They can probably, LISA can probably detect merging supermassive black holes. They can also detect merging white dwarfs, but I'm not going to talk about all this. This is probably for some day in the future. If you're interested, please let me know, and I'll be very happy to answer these questions after this talk. So moving ahead, whenever I'm going to talk about black holes, since you all are astrophysicists, I do expect that you treat this as a pure black hole, not a black hole with charge. So if I say a black hole, it simply means a black hole which is completely characterized by its mass and its dimension is chi. There is not going to be any charge associated with an astrophysical black hole. And if you want to know why this is such a case, you can try to do a homework problem if you want. You can try to calculate the gravitational wave coupling constant. You can try to do what is the electromagnetic coupling constant. If you have done a quantum mechanics course just recently, it is 1 by 137, and try to figure out what is the gravitational coupling constant, and you will get an answer very much soon why we don't have astrophysical black holes to be charged. But anyway, if these two black holes are in orbit around one another, they're completely characterized by a set of 15 different parameters. And these parameters can be broadly differentiated into a set of intrinsic parameters and a set of extrinsic parameters. The intrinsic parameters consist in components, and they govern how the waveform looks like, how the gravitational wave signal parameters, such as the sky location parameters, which consist of light acceleration index, consist of the inclination and the azimuth, or the polarization angle, merger time, will just tell you when the gravitational wave, how loud it is, where it is located, or what is the putative source of the signal, and stuff like that. So the question is, when can or which kind of black holes can actually LIGO, Virgo can detect? So if you want to know that, if you do a naive calculation, you will think that, okay, if the strain or the change in the length in the arm of the detector is roughly greater than 10 to the minus 21, and if the frequency bandwidth of the gravitational wave source is between 10 and 5000 hertz, then we might be able to detect this. Not quite true. If you look into this plot is what is called as noise power spectrum. It quantifies how sensitive your detector is at each and every value of frequency. It is the noise power in a given frequency bandwidth. That's what this quantitative tells me. So if you look into this set, you can pretty much understand that the detectors are more sensitive at between something like 10 hertz and something like 100 hertz and something like 300 hertz. It is not that sensitive at this lower band of frequencies. And although I have not plotted here, if this actually goes up something like this, and it is also less sensitive at very high frequencies. So if the gravitational wave signal is within this sweet spot, something like GW150914 was, then you can do the best physics out of it. If it is something short like GW190521, which was detected on 21st of May 2019, leave the things in the background now. Then it becomes a real challenge to really decipher this kind of sequence. By the way, this was the first event where the merger remnant is actually an intermediate mass black hole. Now, you might have heard about stellar black holes. Stellar mass black holes are black holes which masses less than 100 solar mass. They are putatively formed from stellar collapse. Whereas intermediate mass black holes have masses greater than 100 solar mass, and the upper boundary is dependent on whom you're talking to. So if you're talking to me, then I will say the upper boundary is at roughly 10 to the 5 solar mass. So any black hole that has masses between 100 and 10 to the 5 solar mass is an intermediate mass black hole. And LIGO can only detect the lower end of the mass spectrum, something less than 500 sols, not more than that. Because this signal will move towards this region, which means it will go outside the sensitive bandwidth of the detector. If you have greater than 10 to the 5 solar mass, then you will have supermassive black holes, such as M82 and stuff like that. I think here people are all expert here, so I'm not going to talk about this and destroy it. Anyways, so most of the detections that has been made by LIGO so far publicly, let me tell you, there is no secrets. We haven't detected any more binary neutron star yet. There is a Grace DB alert. If you follow gravitational wave alerts, then you might heard there is a binary neutron star which we might have detected, but trust me, it's not a thing. It has a signal to noise ratio of 6 or 7. It's not. I don't care about those kind of things. Anyways, most of the signals that we have detected thus far corresponds to binary black holes. And in fact, people have got bored with detecting binary black holes. But using these detections, we have been able to study the demography of the binary black holes, namely study its population properties. We have been able to validate general relativity. We have been able to do some bit of cosmology, but that's about it. But time and time again, nature has actually thrown us some sort of swinging yogurt. If you like the cricket analogy, or if you like a baseball analogy, it's called curveball. And that one of those curveballs is actually GW231123, which is going to be most of what I'm going to talk today. So this event, and by the way, you can scan the QR code, and this is a pretty old thing. Now the paper is almost accepted. So this event, the final merger remnant, corresponds to intermediate mass black hole with total mass between either 190 and 150 solar. There is huge uncertainty that you can see corresponding to this. For your reference, GW170817 was really well measured, and that is simply because the signal was pretty long lived. So talking about this event, the first thing that people love to see is a plot that looks like this. So the top panel shows the time domain representation of the signal, and the bottom panel shows the time frequency representation of the spectrogram of the signal. Now, to be honest, I'm cheating a bit. What is actually shown in the top panel is what is called as white noise. So what is done is that we take the gravitational data, we bandpass it, meaning that we throw away stuff that is below a certain lower value of frequency. We also throw away stuff which is above a certain value of frequency, and we just look into a very like filtered data that we have. Once we have the filtered data, we whiten it using the noise power spectrum, and then we inverse Fourier transform it. So there is a lot of data processing that has been done to make this nice, beautiful plot. Anyways, if you look into this nice, beautiful plot, you will see this black colored line. This is the actual data. And these blue colored curves are how where we have fitted the data using our analytical GR waveform models. And you can see it has done a pretty well job. There is some amount of random noise fluctuation that is happening here. This is mostly consistent with Gaussian noise. And if you look into the duration of the signal, it is roughly 0. I don't know, 0.1 second at max. Loosely. And if you look into a time frequency representation, you will see that most of the signal power is concentrated between 20 Hz and 80 Hz. And there is no signal energy beyond these regions, which you can see is completely dark outside. Okay. Now I'm going to teach you a trick. So this is not part of the paper. This is how I do data analysis once I see a signal. So I told you about signal to noise ratio. So the signal to noise ratio is roughly how loud the signal is corresponding to the noise in which the signal is going. Now, normally gravitational wave signals have a strain amplitude of 10 to the minus 18, 10 to the minus 19, and the noise in which it is buried is something like 10 to the minus 6. So as I said, you need to do a lot of data processing to really dig out the signal from that of the data. But once you've done that, you can calculate what is the SNR of the signal. So if you look into this signal, you see that the peak amplitude of the signal is roughly 2.5, right? So if you look at the top value, it is roughly 2.5 times the value. You can also see that the duration of the signal is roughly 1 by 25 of a second. And I will give you one additional input, that the sampling rate, that is the number of samples per second, is something like 10,024. So there is, within 1 second of data, there are 1,024 samples. And if I tell you all this, you can plug in on the value and you can get a value of 16. And this is corresponding to just the Hanford detector. If you have the Livingston detector plugged in, you'll have to multiply it by 1.414, which is square root of 2. And if you do that, can anyone tell me the value? It's 22.4 if you do the math. Very good. How will you do that? 62 plus 2. So this is how one tries to do this kind of data analysis very crudely. But if I give you a chunk of data, let's say 7 days long of data, and I ask you to find the signal, then of course you cannot do this in this particular way. So how do we really look for gravitational wave signals? So there are currently, broadly speaking, 2 different methods. One is the model search method, in which we use an analytical gravitational wave model, and we try to look for the gravitational wave signal as is being done here. We take the data, we take our model, and we try to fit each and every second of the data with that of the signal. So this is what is called as match filtering, broadly speaking. And then we have the minimal model method or the burst search method, where we take the time frequency map of the detector. So this is handput again for you. There is a Livingston detector, and we try to look for any coherent excess in power in the two detectors. In this kind of searches, we are demanding that the signal that we are looking for is what we know. So let's say I have a binary black hole signal, and before performing the search, I'm assuming that I'm going to look for a binary black hole signal. This kind of search doesn't make any sort of assumptions. So let's say there is a supernova explosion that happens tomorrow, then this kind of search will fail to detect it. This kind of search should be able to find it. I won't say confidently that they will find it. There is a lot of configurations and stuff that happens, but they should be able to find this kind of search. This is a much more generic search than these kind of searches. Any questions, Apurva?
Sure. So does this happen while the is on or?
So current, broadly speaking, again, there are two different kinds of searches. One is called as low latency or online searches. So by low latency, you mean that the detector data is observed at, let's say, time X. So within a millisecond or a few microseconds of the time, you should be able to perform these kind of searches with something like 100,000 templates. It's a big data down. But this kind of low latency searches are not really fine-tuned to figure out everything that is happening in the data. For that, we have the offline searches or the higher latency searches, where we have improved data quality information and we perform a much more rigorous kind of search. Search is also done in the same manner. We have the low latency version as well as the high latency or offline archival method of searching. I think in AGN it's called archival searches or something like that, if I'm not wrong.
Well, I mean,
Yeah, data.
these are archival data to do searches.
Any more questions? Now, so the question is how confident that we are that this is a real gravitational wave signal. Now you see that most of our gravitational wave detector data is actually noisy, and it is plagued with a multitude of different kinds of noise sources. It can be due to a person moving around. It can be due to the mirrors vibrating. There can be a different multitude of different ways in which the detector can be impacted. So the question is how confident we are when we have detected a gravitational wave. Of course, the signal to noise ratio is a good measurement, and if you look at the numbers here, it is pretty close to the approximation we made. So we found out that it was 22.4. You can see it is very close to that. There was a small mistake I did in that slide. If you correct for that mistake, it will come out to be exactly this one, 21.4. Anyways, so how do we quantify how confident we are on our detectors? So to do that, we calculate the false alarm rate. It is a quantity that measures how frequently a random noise fluctuation can actually mimic as a signal. So if you look into these numbers, it is called as inverse false alarm rate. So it's the inverse 1 by the false alarm rate. And if you look at this number, it is very, very large. So for example, this number is 10,000 years. What it means is that if you just wait for 10,000 years, then once in 10,000 years, there might be one random noise fluctuation that can actually mimic as the signal is. And if you are a guy who loves sigmas and p-values, you will see that the p-value corresponding to this event is something like 4 sigma. Just so you know, most of the gravitational wave detectors, apart from the first one and GW231123 lies between 3 sigma and 4 sigma. This actually goes beyond 4 sigma. So this really gives us confidence that from a search perspective that this is a true event. And the other fact that we are confident that this is a true signal is that it has been both found by the modern searches as well as the unmodeled searches. Don't worry about the acronyms. They just stand for coherent wave bus, second generation coherent wave bus cross power. They are just names. And here, if you see, it stands for Python-based compact band coalescent searches and other things. You don't need to worry about that.
So what's the difference between the two? In one, you have some modeling, or what is the difference?
So in CBC searches, we have a semi-analytical waveform model and we try to perform match filter searches. In these burst searches, we look for coherent excess power. Now, if you ask me what is the difference between all these four of us, practically saying nothing is different. Only thing is how they treat the noise population. So how well you separate the signal population from the noise population is what differs between them. But other than that, the field work is exactly the same.
But why this what do you call it,
The false alarm.
false alignment is quite
So that's what.
different.
So the way they treat the noise. So let's say if you look into GSPR, the number is quite high. It is because it is able to separate out the signal from the noise much better than that of the price research of the MBTs.
On that reflect in the signal to noise ratio itself.
On the signal to noise ratio level, you see that they are more or less consistent with one another.
So that's what I'm saying. So if you are,
Mhm.
can extract the noise,
Mhm.
which means you are reducing the noise.
Yes. So
Then I will also say my signal to noise ratio is better in that.
So
case.
after the signal to noise ratio, we do a lot of tests. One of them is the signal consistency test. So in there, we actually try to measure how consistent the signal is with the semi-analytical. It's basically calculating reduced chi-square quantity. So at that level, the way GSTR calculates its reduced chi-square is much better than that of chi-square. So once we have this calculation of this signal consistency test, you use those outputs to modify your signal
So
to
it's
noise.
not actually the semi-analytically derived waveform that you are deducing.
Yes, if you can say something. There is lot of other data processing. So for example, GSTL currently also uses a machine learning based algorithm to also suppress the amount of noise content. So after it had performed normal match filter search, it also tries to reduce the background in that particular manner.
Yeah, sorry,
Mhm.
I think I didn't follow quite, but so there is one IFR online and the another one is offline.
Yeah.
What is the meaning of?
So online is the low latency search pipeline and the offline is the archival search pipeline. So in here, when you're performing the archival analysis,
And there can be so much, okay, so
So-
that's
Mhm.
2 into 10 to the minus, so if I take GSTLL,
that's
2 into 10 to the minus 4 in the online,
Mhm.
and greater than 10,000 in the offline.
Yes.
I mean,
And
that's why they-
the jump is because when it was performed online, the template which managed this data was packaged. So when they perform this offline searches, they improve their template bank. So they have much more better coverage within the parameter space within which the event occurred, and that's why this false.
That's the inverse of the,
inverse of the
so that
false.
means low value means that's worse.
Yes.
So it's one part that number is the false alarm rate.
Right. So 2 into 10 to the minus 4 in that sense is meaningless.
Yeah, it is like
Completely
it is
meaningless.
like
Absolute meaningless thing.
yeah. So if you ask me, this is not a difference.
There is not a.
Yeah.
This is a details.
Yes.
Any questions? Now, once we have detected our gravitational signals, we try to infer what kind of source might have produced it. So to do that, we use Bayes' theorem, and I think people here knows what Bayes' theorem is, but I will rephrase anyway. So the goal is to figure out what are the properties of the source that might have produced this signal. So we are targeting what is known as the posterior distribution. But before we look into the data, we make some assumptions of what might be present in the data. So that is what is the prior. So once we have the prior, what we try to do is like for each and every choice for prior value, we try to look into how well this signal or the signal that is sitting in your data can be best fitted with this kind of waveform models. So that is your likelihood calculation. And for today, you can ignore this Z value, which is called as the variance. Now, this is mathematics. Let me give you a real life analogy. So let's say you don't know what is a rhinoceros, okay? And I, who have visited a zoo, probably know what a rhinoceros is, but I am not a really good photographer. So I have just snapped the horn of the rhinoceros and I have given you that horn. Okay. So that is your prior information that I'm giving to you. Now, within that image, you can probably see some leaves in the background. So you know that it is a land animal with some horns. So that is the complete prior information that you have. Now you go to the zoo, you know a priori that it is a land animal. So you don't go to a water kingdom or the birds part or anything. You just go to the animal part and try to look for all animals which has horn. You obviously won't be looking for a unicorn because it's not a real animal. So that is also your prior. And you try to match with each and every age of the animal. So that's how you are calculating your likelihood. And once you find your rhinoceros, that's where the peak of your distribution occurs. So that's your posterior that you're getting as an. So this is hand wavily saying how Bayes theorem works. So the thing is, if you want to infer the binary properties, we have to make certain waveform models because we want to fit the data with this kind of waveform models. Now I'm completely not an expert in this thing. I'm trying to learn it from my girlfriend. So it's going to take a long period of time. But here is roughly what is going on. So what we want is the solution of the two-body problem in general relativity. So if you recall, this is your Einstein equation. It's that there are 10 nonlinear coupled partial differential equation which we have to solve. And solving this numerically is very, very expensive. In fact, if you want to solve this for two binary black holes with 10 orbits, this roughly takes you some 20,000 or more than that CPU hours. So the other alternative to doing this is to approximate the solution using perturbative techniques, which is more or less analytical. So you use post-Newtonian calculations. So you try to calculate the Newtonian stuff and you try to append or modify it or correct for that. But in practice, since this is not really cheap to do computationally, and since this gives you approximate solutions, we combine both these two parts to develop what is known as semi-analytical waveform models. So if you have not seen a gravitational wave signal, this is how it looks like. So we have the adiabatic inspiral part. When we have two slow motion weak field region where two black holes are sort of adiabatically approaching one another. And then within this limit, all our approximations sort of breaks down. So within this part to this part, we completely rely on numerical relativity for figuring out what is going on. And beyond, after the two black holes are merged, it sort of leans down to form a quiescent curved black hole or a stationary curved black hole. And within this region, you can again use black hole to really model this thing. So as you can see, it's a patch up work of multiple different things that has been used for our calculations. So broadly speaking, if you look into the literature, and again, as I said, I'm not an expert. There is we have the answers which corresponds to post-Newtonian calculations, where we try to correct the Newtonian solutions with V by C corrections. We have the post-Minkowskian approach, where we expand the Einstein's equation in powers of G beyond the flat Minkowski. You can just say that this is spin effective one body model, this is time effective one body model, they're not super informative. And then we have the phenomenological model of GW models. These GW models are built by just fitting on data. So you take the signals, and this is what Ajit really formulated at ICTS. So what he did was he took the effective one body solutions and he took just tried to get an idea of how it looks like in a closed form expression like A into E to the I5, and that's how these waveform models are built. And between these two, you can see that there is almost another waveform model, which I call as the surrogate or interpolation models, which lies between semi-analytical and numerical. So how these are built is you take a bunch of numerical relativity solutions, you try to fit their amplitude and phase relations, and you sort of interpolate between these two images. this gives you waveforms which are as good as numerical relativity synthesis itself. Yes, so if
But
you
then the advance, so what's the advantage? I mean, yes, so you have, but to do the interpolation, you need the solutions from numerical relativities.
so currently
Then how are we advantaging in terms of that? I mean,
so
or what is
so
it?
currently the SXs, which is the Cornell and the Caltech group, they have simulated something like 4,000 numerical relativities.
So you just simulate it once and keep it as a repository and then keep extrapolating and
Yeah.
finding things.
Interpolating, not extrapolating.
Sorry, interpolating, not extrapolating.
It's because people claim they can also do good enough job for extrapolating, but they work probably in the near neighborhood region. So if you know what is the solution for q equals to 1, you might predict what might go for q equals to 2, but not beyond that. That's why there is this advantage. Now, if you look into these waveforms, they are time domain waveforms. So what they try to do is they solve the two-body problem using complete semi-analytical approximations, and they give both the conservative binding black hole dynamics as well as the waveforms. This just gives you the waveforms. These are extremely fast. They are frequency domain waveforms, and but the like the fine they pay for the being fast is that they are not that accurate. This is the most accurate, followed by this, followed by this. Okay, now that we have the waveform models, what we try to do is we use it to infer what are the binary black hole properties. So, if you recall, the duration of the signal was 1 by 25th of a second, and which actually means that you have very limited signal information, which tells you why there is a large uncertainty in the source parameter estimate. Other than that, due to the difference in approach in how the waveform models have been, if you try to subtract two waveforms with the same binary parameters, let's say you use one effective body approach, one phenomenological approach, and you try to subtract how two waveforms are in agreement with one another, you'll find that the value is non-zero. Now, if you are not a person from gravitational wave astronomy, you will say, hey, this is not good. This means I cannot use the waveform for our analysis. But in practice, we don't need this to be equals to 0. We just need it to be much, much lower than the noise level in the meter. So if you subtract these two waveforms that we have generated, and if the difference between these two noise waveforms are like less than 10 to the minus 30 or something like that, then you should not worry about this signal. Problem is, for this signal, this was not the case. If you look into this plot shows you the primary mass. The primary mass is the heavier of the two black holes, and in this panel is the secondary mass, which is the lighter of the two black holes. What is plotted in different colors is the different waveform models and how they have been able to capture the binary properties. You can also see a gray shaded region, which corresponds to the fact that you have assumed the primary black hole to be heavier than the secondary black hole. So these blocks away all information which says that the secondary is heavier. And you can see here that the XO4F that was built for the fourth observing run. So that's why O4A completely disagrees with all the other waveform approximates. If you look into the best solution, the inner circuit solution, you can also see that it predicts a system with roughly a total mass between, I don't know, 120 and 150 is, and the secondary component which total with mass between something like 90 and 130. So that's almost everything that you need to worry about in this plot. And if you
Going ahead, so if I can understand, the final wave produced by different model will be similar.
yes,
Then
but the properties are different. Like if you can generate, can I use a pen? So the thing is, let's say you want to generate a waveform H. So whenever you are doing this Bayesian solution, you are actually trying to feed your data to something like this. Now the thing is, because of modeling differences, the same set of parameter theta for a waveform model, let's say W1, may not be equals to this waveform that is generated with, let's say, parameters theta with separate waveform model development. And this is because of the differences in their approach and also because of the differences in the approximations that they make when they develop this wave.
But that's my question. Then it should be at certain regime.
Mhm.
These waveform producers should be better than the other.
Yes.
Isn't it?
Yes, and that is the case when it is non-spinning or when it is GW150914 like, which is very vanilla. So in those cases, the mass ratio is roughly equals to 1 is 1 to 2. And if you look into a total mass of this kind of system, it is like roughly 60 to at max 80 solar mass. You can actually go down. You can actually go down to 20 to 80 solar mass. And if the total mass and the mass ratio is within this region, all the waveform models decrease. If you go beyond that and you have something like total mass of 190 to 160 solar mass, because of you are really fitting into this part of the data, which is the merger down portion, they don't agree with you.
Why is there the mass dependence? What is
The
the
mass is higher, so your gravitational potential is much
No, I
stronger.
understand.
So
If your mass is higher,
Mhm.
means not like orders of magnitude higher.
So,
It's,
so the thing is, I can tell you. In this part is based on post-Newtonian approaches.
Yes,
And when you go to this part, it is the numerical relativity informed. Now, this inner circuit is as good as numerical relativity. If you look into, let's say, V5PHM, which is the SCOD inner model, this actually fits to, let's say, 100 numerical relativity solutions. If you go to these phenomenological models, they fit, let's say, to 20 waveform models, 20 numerical relativity solutions. Because they are not sufficiently calibrated to numerical relativity solutions, they don't perform well in this. So that's why within this part of the parameter space, this high total mass comes into the solution because of this.
but can't we do like, let's say, what we have got from numerical simulations, that parameter range, I can regenerate my waveform in a semi-analytical way and do it better, you know.
Yes, but the semi-analytical waveforms are themselves dependent on numerical relativity. So what you have to do is you have to simulate your inner waveform. You have to take those inner waveform, recalibrate your semi-analytical solution, and then refit into your data.
so the mass scaling is not trivial.
Yes.
No, but now I know from numerical relativity simulation that this is probably the range. Then there I generate more templates.
So as he said, total mass is a scalable parameter. What is problematic is the region where the fitting is the amount number of waveform that you are fitting. So currently, these phenomenological models are not adequately calibrating their simulations to numerical relativity simulations. Once they found this simulation, if you look into the archive papers, you will see that there is quite a few papers that actually tries to do a much more better fit to the waveform numbers within this region. So that's how they are trying to improve their templates. Does it answer your question?
Very good. So
Yeah.
So given that, I will believe that whatever numerical relativity simulation is doing, that I should be believing rather
Yes.
than the other.
Yes. So that's what I am trying to simulate. Because we are not simulations among all other cases. Any more questions?
So as you can see that there is the orange region and the gray region.
Mhm.
They two completely disagree from all the other models. So is there a systematic reason why the first XPHM, XO4 and they are
So this is a phenomenological model. This is another phenomenological model. So this phenomenological model, when they try to calibrate to numerical relativity simulations, they calibrate to just aligned spin waveforms. And by aligned spin, I mean that the two black hole components are aligned with respect to one another, as well as to the orbital level. These XO4A actually calibrate themselves to precessing waveform model, but they don't do it sufficiently well. So there is a systematic difference between these two. So even though they're phenomenological model, because of how they calibrate stuff, this sort of does a better job than this.
and then there is the V5 case and that is also probably a phenomenological.
Yeah, it's a effective one-body model. It stands for Versal Pi Recessing Hydrogen. So it does a much better job than the other two semi-analytical models.
What are those like? So yeah, I can see the contours and then what are those like beads?
For these ones,
No, I can see like light greens, I mean.
Light
that's
green.
right.
Oh, inside, this is a PDF put into a skill. So
That's
that is
words, yeah.
yeah. If you're wondering what these lines are,
That's fine.
they are the
That's
90%
fine, yeah.
credibility. Okay, so given that you are in part of a collaboration and you need to be democratic, what people tend to do is they combine all the posterior samples and they say, okay, I don't trust any waveform model at this point of time. Let's say that my posterior corresponds to a equal weighted stuff. And other than that, we also saw a result for the numerical related simulations, which is NS bucket, which is solved. So if you recall a few slides back, I showed you a plot of 1905-21 and how it looks like. That was the previous heaviest event that was detected by LIGO Volko Kagra during their third observing run, and it had roughly a total mass of 150 swings. This one has a total mass much greater than that. It's between 190 and 260 swings. So this is currently our best, the highest binary black hole that we have detected. Now, for people who have done a little bit of stellar astrophysics, they might recall that there is something called as a pair-instability gap. It is so because of pair-instability process due to production of electron-positron pair, you don't expect to see black holes between total mass of 65 and 120 solar mass formed due to stellar collapse processes. So this is actually demarcated using these orange or pinkish lines that you can see out here. And you can see that both these two black holes, the component black holes, lie spot on within this pair instability gap. So you can see the secondary component is within that gap. You can see that the primary component is almost within that gap. It is actually straddling the gap if you go seeing much more clearly. And if you look into the combined posterior samples, there is quite a bit of support beyond 125 seconds. This is tells you a story about astrophysics. So we are pretty much confident that this is not really a stellar collapse by remnant. This might be found from multiple mergers of earlier stellar remnants that might have happened. We'll come to this later on within this slide. I think I'm not doing good with time, but I will go ahead as fast as I can. So the next thing is what about the spins of the black holes? Now you know from GR that the spins of the black hole cannot exceed 1 because there will be negative singularities. And if you look into these component black holes, we'll see that there is a support for the spin components to be extreme. That is a value of 1 for both the primary and the secondary. And you can see that with if you do the math properly, you see that there is a 91% probability for the component black holes have spin values greater than 0.7. And this is the highest spinning binary black hole merger that we have detected up until now. In fact, the number of numerical relativity simulations which spin greater than 0.7 is extremely rare. And that's also one of the reasons why people don't really trust the numerical relativity surrogate to as good accuracy as now.
Final spin?
Huh?
Final.
Final spin is roughly 0.91 or something like that within the domain.
That's
Yeah, that's a median estimate. Yep. So coming back to the previous plot that have shown quite a bit long back. So using all our gravitational wave posterior samples, we try to fit our data using the simulation that we have generated, and you can see that this is a really nice fit with the data. By the way, this is the all the waveform that we have models we have used. We took all the waveform models and we try to fit with the data, and you can see it does a really good job. So moving ahead, let's come to a bit of astrophysics. So the question is, how can you produce this kind of heavy source? So currently there are two broadly competing models. One is the isolated formation channel, where the component black holes, the primary and the secondary, can be either formed from stellar collapse. And then within due course of time, they evolve together and they merge to form a merger element. So this is what is isolated formation channel. And the second one is what is called hierarchical mergers. So what happens is your primary can actually be a remnant black hole, which is formed from an earlier collapse. Your secondary can also be a merger remnant from an earlier collapse, or it can also be stellar black holes that has formed stellar mass black holes that has been formed due to stellar collapse. Or it can also be due to merger of two stars, which become so heavy that they collapse to form a black hole. So it can be done in multiple different ways. And then in due course of time, it wants to form an object. So
So, I mean, principally, what is the difference between they kind of look similar? I mean, isolated formation. Yeah, these two.
So in isolated formation, the primary and the secondary are direct stellar collapse remnant. In this one, it may be a stellar collapse remnant, the primary component or secondary component, but they have a higher probability that they are formed from a previous merger. Yeah. So coming to GW231123, there is the probability of it, the primary component is greater than 130 solar mass is roughly 74%. And the probability that the secondary component lies between 60 and 130, which is the pair-instability gap, is roughly 83%. Based on these two numbers, we are pretty much confident that this is not really an isolated formation channel. This is more to do with the second generation or third generation or multiple merger formation channel that comes into picture.
So one thing, so.
Yep.
Let's say we have two stellar remnant black holes and they merge, and then again the merged black hole then merges with another merged black hole, and this hierarchical thing goes on. So how many such mergers we expect in Hubble time? Can a black hole?
Good question. So it depends on your host environment. It depends on the mass ratios involved in the system. It depends on multitude of different factors. So for GW231123, this particular thing, we can pretty much confidently say that these two, that is the parent of the primary black hole, or the grandparent of this primary black holes, are stellar remnants. Okay. Now the thing is, within AGMs, you know there are regions called migration traps. Now within migration traps, there can be rapid number of mergers that can be happening within very few million years. However, if you look into globular clusters and stellar clusters, because the escape velocities of those environments are roughly 100 kilometers per second, 200 kilometers per second, after the first merger, one of the merger remnant can actually get ejected from that host environment. So it may not even participate in next generation mergers. So as I said, it depends on a multitude of different factors. Anyways, coming to GW231123, we are pretty much confident that the component black holes are actually second generation black holes, that is, they are from previous stellar collapse. If you do a bit of Bayesian inference, you can pretty much say that the primary component formed from a mass asymmetric merger of 109 and 35 solar mass. There is a huge uncertainty in this measurement because we have very less information. And the same is true for the secondary component as well. And because of the escape velocity, which we are talking about, globular clusters and young stellar clusters are not the putative host environment for this. But other than this, all these analyses that we have talked up to now, we have assumed that the sources are non-eccentric in nature. And this is because we don't have good enough waveform models for this part of the parameter space. So we cannot also rule out eccentricity that is involved within the system, if any.
How much will that make a difference? I mean, if eccentricities are involved.
I'm writing a sort of paper. Okay, I can tell you. So the thing is, so if you say that there is eccentricity involved, then and redo your analysis. So we found out that the component spins can be as low as 0.1. The total mass remains more or less the same, but the component spins almost goes to 0.1. And this is simply because you can mimic a precessing binding black hole with an eccentric binding black hole signal, especially when the signal duration is exponential. Okay. So going to the last part, so given the high total mass of the system, most of the signal was actually ringed down. And therefore, what we try to do is we try to feed the data with a bunch of damaged sinusoids or curved black hole. So why it's called ring down? It simply looks like waveform which can be produced by ringing bells. So that's why it's called ring down. And the third model is where your damped sinusoids are informed by the final mass and the final spin of the black holes. So there is a huge appendix written in the paper we talks about the uncertainty in the start time of the ding-dong signal. And this is again because the signal was actually stopped. But if you try to do your ding-dong based analysis, the Quasi-normal mode actually fits the data quite a bit well, as you can see in the initial part, and then not quite so good in the later part of the data. And this is because there is a huge amount of uncertainty that is involved here. But nonetheless, they actually predict a final mass of greater than 200 solar mass, which means that the merger element is actually an intermediate mass black. And if you look into the combined posterior samples and try to look at different instances of time when we try to feed the data, you can see that depending on the start time of the analysis, there is a huge uncertainty. And this is an open question. We don't know what is going on. And that's why in the paper we have just said that this is what we have observed. We don't know what is going on. Probably someone in the future will solve this. So to summarize, this was a beautiful plot that was made by Simona. So this sort of summarizes this event. So this is the heavier binding black hole that we have observed. The component black holes have masses of 137 and 103 solar mass. And there is a huge probability that the primary black hole, that is the 137 solar mass black hole, actually straddles the mass gap. But the secondary black hole lies spot on within this very instability black hole mass gap. And the potential origin story of this event is that it is a hierarchical merger. And this was observed only by two detectors, LIGO Hanford and LIGO Livingston. No Volvo involved, no carbon involved. And the duration of the signal was roughly 1 minute. With this, I will stop. If you have any questions,
Questions?
How far was this
yes.
thing? I can see that.
13 million light years. There was a huge uncertainty. It was roughly 1.5 gigaparsec, plus minus it goes to 5,000 megaparsec, and something like 800 megaparsec. There's a huge uncertainty.
Nothing has been pinpointed as maybe
Redshift.
the redshift. I didn't.
The host
galaxy.
host.
Galaxy.
there is a paper by Barry McKinnon and Sabik Ford that came out today, that they say that this might be coming from a particular AGN, but it's debated.
AGN?
Yeah, like an AGN host, the host.
Yeah,
is the
host.
AGN.
So some host galaxy, alien host galaxy.
But
Amrojit?
And because in the second modern fit contour for lot of the A1 necessarily. There are two
this one?
second process. In the farther region, there's two big points.
This one?
Yeah, it's a two levels.
I will do a sort of animation. You can see why is the second peak happening. So the second peak is from this. And the first peak is actually coming because the other person was
Because of the problem.
yeah.
I have a question regarding the smaller contour at the bottom. What is?
So this actually means that when you do this sort of sampling business, what we are really trying to do is we are going to feed the data with this. What it means that there is a small region of parameter space that happens for this XO4A revenue that you can see out here that can actually feed. That is what is being reflected in the teeny tiny space.
Is that really?
Huh?
Is that particularly relevant? Then
Yeah, it's within the 90% confidence or the credible, not confidence.
Okay. Other questions? Yes.
So, this is just a general question, like, if you consider all the, black hole binaries that have been detected by LIGO so far,
Mhm.
how does the mass function look like?
Mass function, good. So component mass wise, if I plot M1 here and PM1 here, it sort of looks like this. So the second bomb occurs at roughly between 45 to 60 solar mass. So this is the pulsational pair instability gap that starts here. And this primary peak happens right here 20 solar mass. So, and this secondary peak happens at roughly, I forgot the numbers, but it will be roughly at 70 or 80 billion. So this is how it looks like for the component black holes.
So, okay, great, thank you. So then my question is that, so you are detecting, these black holes, or LIGO is detecting these black holes. And then, as you discussed, that if you go to higher and higher mass, you have this issue with the waveform fitting.
Yeah.
So would it be wise or no, would it be even remotely correct to assume that the reason that we are ending up with these masses is because beyond this mass
Selective.
range, we have issues in detecting and understanding the waveform, or it is just a theoretical that I have to believe that this is how the mass function should be.
So the detection wise, we don't know. When you modeling functions, there are problems because detection wise, as I said, there is an unmodeled approach that sits out
That's
there,
right.
right?
No,
Uh,
that is whether you are detected or not. Signal is real or not.
yes.
But what
But
is the mass?
When you
But
try to
mass.
when you try to do these mass inferences, you have to rely on waveform policy. And other than that, there is also a selection effect. So you're more if you go back quite a lot of slides back, you see that our detector is more sensitive to between this and this region, and if you plug in the values, it actually lies within this sweet spot. So most of the gravitational events that we are detecting are actually having a total mass between 50 and 80 solar mass. So we have a selection effect also.
Okay,
playing-
yeah, this I have heard about that,
Mhm.
there's a selection effect, but then theoretically.
Mhm.
What is the prediction that, how do you expect the mass function to look like? Is it, I mean, because there is no prediction, because there is no theory that how are these black holes form.
Yeah.
But still, if you think of, collapse of supermassive stars and some of the seed black hole formation scenario in the early universe.
Mhm.
Is there a prediction of how should the initial mass function look like?
So all these feeds are completely data-driven.
Yeah.
Okay. So currently there are multiple models. This is called as the power law plus peak model because you have a power law distribution here and then there is a peak. You have multi-peak model which also fits the data well. And then there are other waveform like other sort of fitting models that happen. Currently we don't know what is the real issue.
Okay, other question, Ridhakar?
Can you explain the templated search or the matched filter?
One sentence.
No, one second.
If you know what PSS is in there. Okay.
1 second.
Okay. Anyways, so what we have done in this match filtering is the following. So we have the gravitational data that is sitting out here, it is in black. And this purple color line is the semi-analytic